Continuity versus differentiability, the converse. Hello everyone. Let's begin by recalling what we covered in our previous subsection. We established a fundamental theorem which states that if a function is differentiable at a specific point, it is guaranteed to be continuous at that same point. Now, this leads us to a very natural and important question. Does the reverse of this statement hold true? To put it simply, if we know a function is continuous at a point, does that automatically mean it must also be differentiable at that same point? The answer, quite simply, is no. In mathematical terms, we say that continuity is a necessary condition for differentiability, but it is not a sufficient one. This means that while you cannot have differentiability without continuity, having continuity alone is not enough to guarantee that the function is differentiable. Over the next few slides, we will explore the geometric meaning of this distinction and look at a classic mathematical example to see exactly where this logic breaks down. Conceptual understanding, smoothness versus connectedness. Now that we have established that continuity does not necessarily guarantee differentiability, let us look at this from a geometric perspective to better understand the distinction. To begin, let's consider what continuity looks like on a graph. In simple terms, continuity means that the graph of the function is connected. A good way to visualize this is to imagine drawing the curve on a piece of paper. If you can draw the entire line without ever lifting your pencil, the function is continuous. This means there are no sudden holes, no jumps from one value to another, and no vertical asymptotes breaking the path. However, differentiability is a much stricter requirement. For a function to be differentiable, it is not enough for the graph to be connected. It must also be smooth. This means that as you move along the curve, there are no abrupt changes in direction. Specifically, a differentiable curve cannot have any sharp corners, cusps, or vertical tangents. To make this concept more intuitive, let us use a real-world analogy. Imagine you are driving a car along a road. If we say the road is continuous, it simply means there are no gaps or collapsed bridges in your way. As long as the road is continuous, you can physically drive from point A to point B. But if the road is differentiable, it means the turns are designed as smooth, sweeping curves, allowing you to maintain your speed and steer gradually. Now imagine the road has a sudden, sharp, V-shaped turn. In this scenario, you are still on the road, so the path is still continuous. However, to navigate that sharp point, you would have to come to a complete stop and pivot the car instantly to change your direction. That sharp turn is the perfect representation of a point where a function is continuous, because the road is still there, but not differentiable, because the direction changes too abruptly for a smooth transition. In the next few slides, we will move from this conceptual analogy to a formal mathematical demonstration, using a specific function to prove this point. Mathematical demonstration, the absolute value function. Now that we have established the conceptual difference between a connected road and a smooth road, let us move from the analogy to a concrete mathematical example. The most classic example, used to demonstrate that continuity does not necessarily imply differentiability, is the absolute value function, denoted as f of x equals the absolute value of x. To see exactly where the sharp turn we discussed earlier occurs, let us examine this specific function at the point where x equals 0. Step 1. Defining the function. Now that we have introduced the absolute value function as our primary example to test the relationship between continuity and differentiability, let us look at its formal mathematical definition. The function, f of x equals the absolute value of x, is expressed as a piecewise function because its behavior changes depending on the value of x specifically. F of x equals x if x is greater than or equal to 0. However, if x is less than 0, the function is defined as f of x equals negative x. It is important to have this precise definition in place, as we will use these two separate cases in the following slides to mathematically verify whether the function is continuous and differentiable at the origin. Step 2. checking for continuity at x equals 0. Now that we have defined the absolute value function as a piecewise function, let us move to step 2 and determine whether it is actually continuous at x equals 0. To establish continuity at x equals 0, we must verify a fundamental rule. The limit of the function as x approaches 0 must be exactly equal to the actual value of the function at that point. First, let us find the value of the function. When we substitute 0 into the function, the absolute value of 0 is simply 0. Therefore, f of 0 equals 0. Next, we need to examine the limits from both sides. Let us start with the left-hand limit. As x approaches 0 from the negative side, we use the piece of the function defined for x less than 0, which is negative x. The limit of negative x as x approaches 0 from the left is 0. Similarly, let us look at the right-hand limit. As x approaches 0 from the positive side, we use the piece of the function defined for x greater than or equal to 0, which is just x. The limit of x as x approaches 0 from the right is also 0. Because the left-hand limit, the right-hand limit, and the function value are all equal to 0, we can conclude that the function f of x equals the absolute value of x is indeed continuous at x equals 0. Now that we have confirmed the graph is connected at this point, we can proceed to the next step to see if this continuity also guarantees that the function is differentiable. Step 3. Checking for differentiability at x equals 0. Now that we have established that the function is continuous at x equals 0, we must determine if it is also differentiable at that same point. For a function to be differentiable at x equals 0, the left-hand derivative and the right-hand derivative must both exist, and, crucially, they must be equal to one another. Let us begin by calculating the left-hand derivative, which we refer to as the LHD. To do this, we use the formal definition of the derivative by taking the limit as h approaches 0 from the left. The formula for this limit is the function of 0 plus h minus the function of 0, all divided by h. Now, this is a critical point. Since h is approaching 0 from the left, h is a negative value. Because of the definition of absolute value, the function of h, or the absolute value of h, is equal to negative h. Substituting this into our limit, we get negative h minus 0. All divided by h. This simplifies to negative h over h, which results in a left-hand derivative of negative 1. Next, let us calculate the right-hand derivative, or the RHD. For this part, we take the limit as h approaches 0 from the right. Using the same derivative definition, we again look at the limit of the function of 0 plus h, minus the function of 0, all divided by h. In this instance, since h is approaching 0 from the right, h is a positive value. Therefore, the absolute value of h is simply h. When we plug this into our expression, we get h minus 0, divided by h. This simplifies to h over h, giving us a right-hand derivative of 1. As we can see, we have two different values for our slopes. In the next slide, we will discuss what this discrepancy means for the differentiability of the function. Step 4. Conclusion. Now, let us look at the results of the calculations we just performed in the previous step. We observe that the left-hand derivative equals negative 1, while the right-hand derivative equals positive 1. Because the left-hand derivative is not equal to the right-hand derivative, the overall limit of the difference quotient, which is the limit as h approaches 0 of the function of 0 plus h minus the function of 0, all divided by h, does not exist. Consequently, we can conclude that the absolute value function, f of x equals absolute x, is not differentiable at the point x equals 0. This mathematically proves the point we touched upon earlier. While the function is continuous at this point, the abrupt change in direction, that sharp corner we discussed, makes it impossible to define a single, unique tangent slope at the origin. Key takeaways. Now that we have worked through the mathematical proof, let us summarize the key takeaways from this section. First, we reiterate the fundamental theorem. Differentiability implies continuity. This means that if a function is differentiable at a specific point, it is guaranteed to be continuous at that point as well. However, as we have just demonstrated, the converse is not true. Continuity does not necessarily imply differentiability. In other words, a function can be perfectly continuous at a point, yet still fail to be differentiable there. From a geometric perspective, when a function is continuous but not differentiable, it usually manifests as a sharp corner or a kink in the graph. This brings us back to our earlier analogy of the road. While the road is connected and you can drive across it, the turn is too abrupt to be considered smooth. The absolute value of x is the primary example used to illustrate this concept. As we proved in the previous steps, the absolute value function is continuous everywhere, but it is not differentiable at x equals 0 because of that sharp V-shape at the origin. Common mistakes. Now that we have walked through the mathematical proof, let's conclude by discussing some common mistakes students often make when dealing with these concepts. First, be careful about assuming the converse of our theorem is true. It is a very frequent mistake to believe that if you have proven a function is continuous at a point, you have automatically proven that it is differentiable there. As we saw in our example with the absolute value function, continuity is necessary, but it is not enough. Therefore, whenever you suspect a graph has a sharp point or a kink, you must always check the left-hand derivative and the right-hand derivative separately. Secondly, do not confuse the limit of the function with the limit of the derivative. It is important to remember that continuity depends on the limit of f of x as x approaches a certain value. On the other hand, differentiability depends on the limit of the difference quotient, which is f of x plus h minus f of x, all divided by h. These are two different mathematical processes checking for two different properties: connectedness versus smoothness. Finally, when performing the actual calculations, be mindful of the sign of h when you are calculating the left-hand derivative and right-hand derivative for functions like the absolute value of x. It is critical to remember that for the left-hand derivative, h is less than 0. Forgetting this sign change will lead to incorrect results, as the sign of h is exactly what determines how the absolute value expression is expanded. Keep these pitfalls in mind, and you will be able to distinguish between continuity and differentiability with confidence.